Right, so thank you for having me here. I'm Tung Lik Lee from the University of Hull, and I would like to present some of the key outcomes from our collaboration with NGINX that involves the residual stress measurements in sprayed steel. Now, the work that I'm presenting here is part of a joint project between University of Hull and Oxford University, and is funded by Bao Steel from Shanghai, the largest steel company in China. Now, let me first highlight the key takeaway points from this talk. Now, in general, when we measure residual stress, especially, a non-destructive method is ideal to measure the true nature of this residual stress in a component. However, it is due to this non-destructive nature as well that we may miss some of the hidden features in a component that could affect residual stress, such as porosity. Therefore, we manufactured a sprayed component with a step change in terms of porosity to allow us to study a correlation between porosity distribution and residual stress distribution. Point number 2. Pseudo-strains caused by incomplete filling of the gauge volume in a sample has been widely discussed and accepted. But porosity, in other words, absence of material in tiny parcels within a component, can also lead to incomplete filling of the gauge volume. And to the best of our knowledge, this has not been widely discussed or explicitly discussed, especially for sprayed steel. And in our case, we considered porosity-induced pseudostrain in our work using our sprayed steel. So I will now introduce the spray forming technique by showing a video of how the metal spray is created in this casting process, and that is through atomization. So the liquid metal flow is disintegrated when it is subjected to high velocity and high pressure gas flow that is channeled into the spray chamber from the nozzles surrounding the molten metal flow. Now, the initial upwards motion of the molten metal is due to a low pressure and recirculating gas region. And in this region as well, we can see that the liquid metal flow is torn into ligaments, which then subsequently form the tiny droplets. And these droplets are subjected to high cooling rates in this gas flow field. Now, to give you an idea of the droplet sizes that we are talking about, this is the size of a typical head of a housefly. And these are the atomized powders or droplets, which is about 5 or 10 microns. For a typical spray, we can expect a droplet distribution size of 10 to 250 microns. And depending on this size as well, we could have a spray that has droplets that are solidified or in a semi-solid state with different liquid fractions. We can then harness the droplets in this spray by placing a substrate underneath the spray to form our component. Now, depending on how we manipulate the motion, the angle, and the shape of this substrate, we can then form components with different sizes and shapes. Therefore, spray forming offers benefits in terms of flexibility and the reduced and simplified steps to produce near finished product shapes, and has found applications in industry, such as to produce the cylinder liners for automotive engines. Now, the benefits of this technique extend to the material properties of the products. Due to the high cooling rates of the droplets, dendritic and cellular microstructures are formed within these droplets at a very fine scale. Now, when these droplets are deposited and consolidated, this microstructure transforms into a fine equiax microstructure, and therefore enhancing the material properties. So far, so good. But what is stopping this technique from being widely used in the industry? like many other casting processes, spray forming has its own downsides as well. And one of them is porosity. In its as-cast form, shrinkage porosity especially can form at the interface between the substrate surface and the deposited metal. And this is due to the large temperature difference between the cold substrate and the deposited hot molten droplets, which cause insufficient droplet remelting. And we can see the effect from the solidified droplets in some of the pores at the interface. So as the deposited material progressively builds up, the temperature of this component gets higher, and that leads to increased droplet remelting, which then forms a region of dense material. At the surface of this component, it is subjected to gas cooling, therefore leading to increased porosity level. Now let's take a look at this in action. So we have a cross-section, a typical cross-section from a sprayed component. And these are the corresponding optical micrographs stitched to show the porosity. At the interface, due to the initial large temperature difference, you can see that we have a solidified layer formed, but it was initially delaminated from the substrate surface. Now as the component's temperature heats up, this solidified layer sticks onto the surface, but it is still relatively cold, forming the porosity at the interface. At the surface, we can see that it is subjected to gas cooling based on the difference in intensity. So by controlling this process, we managed to produce or manufacture a sprayed component with a step change in porosity by spraying in a multiple pass manner. The first few passes being a very hot spray to create the dense material, and the subsequent few passes being a relatively colder spray to produce a porous layer. And this is due to the reduced liquid metal hydrostatic pressure in the tonnage. We then cut ring slices out of this component with 10 mm wide and 20 mm thick ring slices. We then etched the rings to reveal the porous outer layer. Subsequently, we extracted samples to measure the porosity distribution across the thickness using X-ray computed tomography with one of our micro CT scanner at home. And this shows the porosity programs across the thickness of the ring. So here we can see a 3D reconstruction of the sample surface. And we could roughly see the dense to porous transition region. Let's remove the sample surface so that we can have a clearer view of the porosity in the material. We can then quantify the porosity distribution in three-dimensional form. And therefore, for our sprayed steel, we have a step change of about 10% in porosity. Using this tomography results, we then characterized our residual stress distribution using diffraction. And neutron diffraction was selected based on its capability to penetrate into thick metallic components. Our setup at NGINX measured 3 strain components across the ring thickness: the radial strain, the hoop strain, and the axial strain. The stress sample that we used was a 5 mm thick block section from a similar ring. And here it is suitable for me to touch on the porosity-induced pseudo-strains. Let's take a plain view from the highlighted cross-section. So the gauge volume used in this study was a symmetrical one. And pseudo-strain are caused by the shift in neutron-weighted center of gravity from the geometric center of gravity of the gauge volume. For a completely filled gauge volume inside a sample, we can expect the neutron center of gravity to be aligned with the geometric center of gravity. And therefore, we can assume there will be no pseudo-strains. What if we scan towards the surface, let's say to the interface? We then have a incompletely filled gauge volume, leading to a shift in the neutron center of gravity. We can calculate this shift by, we can estimate this shift by using a weighted center of mass calculation. And this shift causes pseudo-strain, which is dependent on the neutron flight path change, delta L, and the angle change, delta theta. Right. So what if we have a porous layer in our sample? As the gauge volume enters the porous layer, the neutron center is shifted to the denser part, leading to pseudo-strain. Comparing to scanning out of the sample, pseudo-strain caused by porosity are much smaller. Now, what if we just considered scanning inside our sample? In our case, we estimated a shift in the neutron center of gravity that led to a maximum pseudo-strain of about 35 microstrain, which is about 1/5 of our neutron diffraction measurements uncertainty. For other components with much more significant porosity, and in a case where the pore sizes are large and gauge volume are small, this should definitely be considered and taken into account. And with the recent ISIS development for tomography-driven equipment and technology, I think this could be achieved relatively easy. So from our diffraction results across the ring thickness, we managed to identify martensite and austenite as our main phases in our aspirate steel. Now at the porous region, we managed to pick up higher martensite content due to the higher cooling rate. We then quantified the phase weight fraction distribution across the thickness of the sample for the stress-free and the ring sample. We can then use this phase weight fraction distribution across the interface, the distance from the interface, to help explain the stress development in our sprayed steel. Now, in general, for sprayed form materials, the residual stress is caused by thermal stress during cooling. And thermal stress is caused by the difference in the mismatch in material coefficient of thermal expansion. Let me give you an example. What if we bond a high CTE layer with a low CTE layer and cool it down? For measurements, let's have the individually cooled length on the screen. Now, during cooling, the high CTE layer shrinks much more than the low CTE layer, but it is now constrained by this layer, causing a tensile stress in the region. So in our sprayed steel, we have a distribution in phase weight fraction. And we discretize the thickness of the sample. And using a rule of mixture, we calculated the effective coefficient of thermal expansion for each layer. And therefore, we get a CTE distribution. We then developed a 3D finite element model to help us simulate the thermal history and the temperature distribution across our ring sample. And in our model, we incorporated the measured and calculated CTE distribution in addition to the physical properties of the materials. And here we see the hoop and radial residual stress distribution across the thickness of our sample. And they were done for the measured results and our simulated results. Due to the high CTE in the dense region, we can expect a tensile stress and a compressive stress in the porous region. Now the differences towards the interface between the measured and the model result is most likely due to the stress relaxation from the cracks in the interface. So therefore, using neutron diffraction and X-ray computed tomography, a correlation between porosity distribution and residual stress distribution was revealed, which suggests a stress reversal or a steep stress gradient across a dense to porous transition region. Now it should be noted that it doesn't mean that you will get compressive stress in the porous region, and it all depends on the alloy and the phases formed in the different regions. And finally, I'd like to thank Jiao Weimi, the project leader, for his continuous support and contribution, Shuyan and Saurabh for their dedicated assistance and advice, and our project collaborators. And lastly, for more information, you download an open access copy of this published work from my personal website. Thank you.
Very nice talk. And any questions to Tao?
Yes.
In the spray forming, you mentioned it's possible to change the temperature of the spray.
That's right.
Can you change the flow rate as well?
That's right. We changed the
Okay.
flow rate, and then we changed the temperature of the spray, essentially.
What was the size range of your pores?
About 200 microns.
That's the average size.
Average, yes.
More questions? Okay, so thank you.